Record. Super. I'm just going to leave this here, and if it's in anyone's way, let me know. Okay. Nope, we're not sharing. Awesome. Share screen. Haha. Okay, so if anyone didn't do the attendance, pretty please do so. Yeah, so if you just take your phone and like you open the camera and you go like that, like on it, a link should pop up on top of it. But also the service in here is actual trash, so it might not. Let me know if it doesn't pop up. Okay, perfect. So I'll just send you guys an email with the link, and how about you fill it out? All right, cool. Anyways, so let's do the thing. Okay, what a mess. Have I ever mentioned that I hate technology? A couple times, yeah. All right. Okay, cool. Nope, you can't see what I'm showing. All right. Please. Yes, okay. And it only took 5 minutes today. We're going places, everyone. All right, so last time we talked about homotopic versus heterotopic and antiotopic, diastereotopic, and then we did some practice with this. Does anyone have any questions, comments, concerns, anything like that about what we've done up till now? Okay. Also, if this is in anyone's way, I broke one of these ones, so I'm not going to try too hard. Yes? I can try. The issue with last week's recordings was it recorded to the cloud, and now I can't download it. So I think I might end up sending you guys the link to the page to view it. I'm not really sure how it works. Do you know how it works?
So if you go into your Zoom, just log in, but not your camera.
Yeah.
Okay. Go to recordings. You'll see them listed. Go to share, and you'll be able to share the link.
Oh, sweet. Okay. Thank you, Leah. I will do that then. If someone wants to send me a reminder email, that'd be cool because I am only like 25% here. That's fine. Any other questions? Awesome. So, today we're going to move on and we're going to talk about chemical shift a little bit. And what do you guys remember about chemical shift? Either from lecture, Orga 1, or from what we talked about last time. This makes me sad. Exactly! So the chemical shift is just telling us the position of the signal. And when we talked about chemical shift, like what was the units? Yeah. Heck yeah, that's already written. So I'm just going to say ppm equals units. Cool. All right, so we're going to talk about carbon NMR and hydrogen NMR because they are a teeny bit different. So let's say that this one is H1 NMR. What is another name for the aliphatic region? Do you guys remember? The alkyl region. Perfect. All right, so does anyone remember whereabouts the alkyl region is? Yeah, some textbooks say 0, some textbooks say 1, so we're just going to say 0 to 2.5 ppm. And so what kind of hydrogen counts in the alkyl region? Yes. Perfect. So we're going to say something like this, right? And the key here is it's a hydrogen attached to a carbon, and that carbon is only attached to other carbons and hydrogens. So the carbon that this hydrogen is directly attached to is not going to be attached to any other weird groups, just other carbons and hydrogens. Does that definition kind of sort of make sense? Okay. Heteroatom. Remind me, what's a heteroatom? Cool. So basically anything that's not a carbon or a hydrogen. So it's our oxygen, nitrogen, phosphorus, etc. Specifically for this class, you want to know oxygen, nitrogen, fluorine. Anyone have any idea what ppm values this is? 35. Cool. And what kind of hydrogens go in this region? That's one of them, absolutely. So I'm actually going to do this in a different color, because I like to color code things. So what Leah said is we have a hydrogen which is attached to a carbon that is attached to a oxygen or any heteroatom, right? But it's really cool because in this example, there's actually another hydrogen that's in the heteroatom. Can you guys guess which one it is? Wait, what? Say again? I don't think I heard you properly. No, but good thinking. So this is the one that trips everyone up, right? So we're going to count the hydrogen directly attached to the heteroatom, and then we're going to count one carbon away. So we only go up to one carbon away. So we can summarize that, and we can say that a hydrogen is in the heteroatom region when it is attached to a heteroatom, or when it's attached to a carbon directly on a heteroatom. I never once give myself enough space in these boxes, so please get used to this. Does that definition sort of kind of make sense? Any questions at all? Okay. So next up, double bond. What do we think goes in the double bond region? Double bonds! Wow! We're all sleeping, guys. I know it's Monday, but let's get some energy. Sorry, I know I'm being annoying. I'm just really happy. So, on a double bond, sometimes we have hydrogens. So, any hydrogen that's directly attached to a double bond counts in the double bond region. So, we can say directly on a double bond. And what do we think the ppm region is? Yeah, approximately 5 to 7. Coolio. So, Dr. West was like asking you guys some really random aromaticity questions on the first day, and it was like, whoa, dude, like, we haven't learned that yet. What molecule do we know that is aromatic? Benzene! Benzene is our best friend. So, for the purposes of this chapter, aromatic equals benzene. And any hydrogen attached to that benzene ring, or any aromatic ring, will be in the aromatic region. So it's important to note that after the heteroatom region, there's no more of that like one carbon away rule. For the double bond and aromatic, it has to be directly on the double bond and directly on the aromatic ring. Okay? Cool. So what's the ppm region for this? 7 to 9, 7 to 8.5-ish. Cool. Last but not least, carbonyl. So what are some functional groups we know that have carbonyls in them? Aldehydes, ketones. Wait. I'm sorry. This is fine. No. Okay, so I heard aldehyde and then I stopped paying attention after that. Ketones. Okay, what else? Carboxylic acids. Awesome. Esters. Cool. Okay. I think there's like one more that you guys should maybe be familiar with. Ethers. Cool. I'm not going to draw those last two out because you don't really need them right now. Ketone and carboxylic acid. So hello to everyone who just walked in. You guys are here for Orgo 2, right? Okay, cool. I just heard some confusion. I was like, Anyway. So before you write anything down for this carbonyl region, we are going to talk about it for a moment. I'm going to make a page. Okay. We have an aldehyde. We have a ketone. And we have a carboxylic acid, right? So when we're looking on HNMR, you really have to figure out like which hydrogen are we looking at, right? It's like you can assume that if he just gives you this molecule and he's like, what's the ppm value, right? You're talking about this hydrogen. You're talking about this hydrogen. And you're talking about these hydrogens. Why do you think I say that? What's special about those hydrogens? Yes? Yeah, that's true. It's all one signal. But something else. Not necessarily, because this one is directly attached to the carbonyl. Right? Exactly. So those are going to be the most deshielded or the only hydrogens available. So this guy is directly attached to the double bond, whereas this carbon is full of hydrogens that are further away. These two are exactly the same because there's symmetry down the middle, right? And then obviously this one is on an oxygen, right? So now we have to figure out of these three, which one is the most deshielded. So let's say this is A, B, and C. And we're going to do a poll because I know those are my favorite. So who thinks A is the most D-shielded? D-shielded is towards a higher number, yes. How about B? How about C? Wow. Okay, so let's talk about it. So someone who said C, why do you think it's the most D-shielded? It is directly attached to an oxygen. Good point. What do you think? Okay, perfect. So there's two keywords I'm really looking for here. Induction was one of them. So inductive effects. And what's that one word that's the answer to everything that starts with an R? Resonance. Perfect. And these two are basically, if you have no idea, like if I ask you why something happens and you're like, I don't know, guess one of these two and odds are you'll be right. The reason that's what we're The reason that's what we're working with is because this bond, excuse me, I'm being dumb. These electrons can turn into a double bond, which can move these electrons here, right? So that is resonance. And we would get something that looks like this. Right? Any questions on how I did the resonance there? Can anyone not see and wants me to zoom in? Okay. So, the next one, this doesn't really have much resonance. Like you could go like this, and you could go like this. But there's something else in play, and someone already mentioned it's inductive effects. So, we're not going to go too deep into inductive effects. All I need you to know is that CH3 groups are going to donate a little bit of electron density. So this group, through induction, which I'll make a different color, is going to donate some electron density. Right? Same here. It's going to donate some electron density. That's also going to work here, right? But resonance is a stronger effect than induction, so we're going to ignore induction for that last one. Any questions about what I've drawn so far? Okay. Is anyone just sitting here like, okay, cool, those are different things, but like how do they get put together? Thank you for being the one honest person. Cool. So the way we put that all together is that this hydrogen has all these electrons being pulled so far away from it, right? So through resonance, the electron density is being pulled in the opposite direction of that hydrogen. So this guy is going to be super duper D-shielded. Whereas this one, yes, it is being pulled away, but the effects are not as crazy. And there is some electron donation from this side, so it's less so being pulled from this side. So between A and C, which one do we think is more D-shielded? C, cool. Now what about B? B is a little bit weird. Yes. It does kind of. Okay. Why do you think so? Okay. So what is the hydrogen attached to? A carbon. And what's that carbon attached to? Nope. Bam. Okay, ready? This hydrogen is attached to a carbon, And this carbon is only attached to a carbon and 2 hydrogens. So this is kind of a catfish. This is not even in the carbonyl group at all. This is going to be in the alkyl region. I see a lot of people being like, what? Do you want me to explain that one more time? Yes? Okay, cool. So A and C are directly part of the carbonyl because A is directly attached to this double bond and C is directly attached to the oxygen, which is attached to the double bond, right? Whereas these hydrogens, they're part of a ketone, which means they're attached to a carbon, and that carbon is then attached to the carbonyl. So that's not really part of this carbonyl structure. It's kind of just hanging out onto the side. So instead of being in the 9 to 12 carbonyl region, it's actually just going to be a super deshielded alkyl region. So it's around, it's around 2.5. And you guys had already told me that C is more deshielded than A, so you were totally right with that. C is going to be approximately 12 ppm, whereas A is going to be approximately 9 ppm. Yes. Yeah, my bad. So going back here, we're going to say that the range is 9 to 12 ppm. Wow. ppm. And only these guys are going to be part of that range. And I'm going to go ahead and add our ketone here with a note that says 2.5. Yes. That's just like what the textbook says is the carbonyl range. Yes. Yes, but that's going to be a little bit later at the end of this week or start of next week because that's when you're putting more things together. But for the most part, if he asks you a question, it's within these ranges. The biggest thing he tries to trip you up on is the ketone. And a lot of times people put the ketone in the carbonyl range. Okay. Any questions? All right, well, I am going to give you like a minute to write this down. Relax your brain, whatever. I really just want a sip of coffee. Yes. No, you are totally right. So the question was, if we have an aldehyde, right, we just said that this hydrogen is around 9 ppm. And then the question was, does that mean everything here is at 9 ppm? No, absolutely not. So these guys, just like the ketone, are attached just to a carbon. So that means these ones are around 2.5 ppm. That was a great question.
So essentially, we're just going to compare. So the hydrogens are attached to a carbon. We need to just pay attention to what that carbon is attached to.
Yep, exactly. Okay. So if we're sure we got this hydrogen stuff, yes, what's that? Yeah. Yes. Yeah, of course. So you're very welcome. So we want to say that it is directly attached No, you know what? That's a terrible way. Let's do that. I'll be more specific. Attached to the carbonyl carbon or attached to the oxygen of a carboxylic acid. I'll zoom out so you can see the whole thing together. Ta-da! Okay. So I see a couple people writing and typing and stuff, so I'm going to give you like another minute, and then we're going to do something even more annoying. Yes. I'm so glad you asked. Okay. Sorry, I'll go back. I will, I promise. So shielded and de-shielded. The way they explain it in lecture tends to not make any sense because they use science words. I do not. So pretend we have two molecules, right? And these two molecules are just chilling, and then all of a sudden, a huge war erupts, right? It's like a zombie apocalypse. One of these guys has a huge defense system, which is called its electron cloud, right? So it has this huge wall of defense. Whereas this sucker, the blue guy, has like a picket fence that's like barely holding. This is like a brick wall. This is like a picket fence, right? So the more shielded something is, the more protected it is from its environment. So if you hit it with like 10 shields, or not shields, excuse me, 10 arrows, and you're trying to stab him, only one of those arrows is going to go in. Most of them are going to bounce off, right? Versus de-shielded, if you throw a bunch of arrows, most of them are going to hit him because his defenses are so weak. So how we can kind of correlate that to the numbers is the more shielded you are, the less things are going to penetrate the shield and hit you. Versus the less shielded you are, the more things are going to penetrate the shield and hit you. Welcome. Any questions about that? Perfect. Okay. So, as I mentioned in the beginning of the session, we do have carbon NMR to also look at. And the carbon NMR numbers are in your book and in his lecture. So I'm not going to spend too much time going through all the specific numbers. I just want to compare one super important thing, which is, again, the carbonyl region. So we already said that the carbon region in HNMR contains ketones and carboxylic acids. And we said the ketone was where? Exactly, cool. So then the aldehyde is approximately what number? It is between 9 and 12, but what's it closer to? 9, cool. What about the carboxylic acid? Cool. Now, when you get into the carbon NMR, things change a little bit. Okay. So we're going to use those same 3 examples to start out with. We have our ketone. We have our aldehyde. We have our carboxylic acid. So what's the biggest difference between carbon and hydrogen NMR when we're comparing these sets of compounds? Yeah, exactly. One of them is looking at a carbon. Sometimes when I ask a question and it seems really easy, I'm not just trying to trick you. So here, instead of looking at the hydrogens, we're looking at these carbons, right? Okay. So what were the 2 words that we used to describe everything? Yes, so resonance. And what else? Induction. Cool. So as far as resonance goes, which of these guys has the most significant resonance? The last one. Let's call it A, B, C. Cool. So the resonance, just like we drew before, goes like so. So what about A and B? What effects do they primarily have? Induction, cool, because their resonance is just this puny thing. So they're mostly getting induction from their methyl groups. And just for the record, it doesn't have to just be a methyl group. It can be any carbon group. So, induction and induction, right? So I want you to take a look at this. Turn to the people around you. I know, talking is scary, but I want you to just talk for like 1 minute or so and figure out from most to least shielded. Okay, so you're gonna look at A, B, and C, and you're gonna rank them in order of most to least shielded. Yeah, we're talking about the carbon now. I honestly just skipped that. Sounds like it's gonna take too long.
Literally was my favorite.
I truly don't know how to say. Wait. Okay. So, someone tell me what you think. Yes.
So I just put B as more than A. C meaning that B is more shielded than A. A is more shielded than C. Meaning that C is the most
De-shielded. Okay, well, thank you very much. Does anyone else want to agree or disagree with her? Like I said the first day, I only hear things you don't want me to hear, so I have no idea what you just said. Say it a little bit louder, please. I know it's you. Go ahead. Okay. Okay. Yes. Okay. Okay, and perfect. And I love that as soon as you said it, everyone was like, yeah, that's what I was thinking, but I didn't want to be the one to say it. You're right. So I really liked your reasoning for C being the most de-shielded, and you are correct. So, most de-shielded. And then between A and B, you guys both picked B, which I kind of get because of what we talked about in the last one. However, what Luke... Yep, okay, cool. So what Luke... I'm trying so hard. What Luke said was there's a lot of arrows, so he's going to go with this one. And while that's not the scientific way of thinking, I like it. So, we're looking for more shielded, right? So we want more... Oh, yes, but we want more induction, right? Hold up, wait, hold on. Don't write this down. I wrote it backwards. You were right between A and B, right? So between A and B, A is the more shielded one, and B is the less shielded one, because this one has more induction than this one. I got so excited by your guys' answer that I forgot that that was a trick question for a moment. But okay, so this is a trick question, and C is actually the most shielded. Oh, yeah. Does anyone want to take a guess at why that is? Hell yeah. Did you want to say the same thing? No. Okay, what did you want to say? Okay, but do oxygens donate or do they steal electrons? Okay, depending on the situation, you guys are right because I got a 50-50. But usually in this kind of stuff, they're electronegative. They want to steal electrons, right? So the reason that that is super shielded is because the resonance effect goes like this. So the electrons are constantly going like this. And so they're not going to the carbon, right? They're not stopping at the carbon, but they're constantly going across the carbon. So we can say that the carbon has that electron density at least a lot of the time because resonance is constantly flipping between the two. I hope I didn't completely confuse anyone. I'm so sorry. Okay, let's go. Let's go through it one more time. Pretend I never got excited in the beginning. All right, ready? We're gonna take two. Yes. We're getting there. Okay. So the actual order is C is the most shielded, and then it's A, number 2, and then it's B. I'll run through it one more time because I know I confused some people. So the reason C is actually the most shielded is because resonance effects trump inductive effects. We already said that, right? And in this case, it's different than the hydrogen because the electron density is just being pulled away from the hydrogen, but it's being pulled towards that carbon because the electron density is going like this. Right? And then when we compare A and B, A has the most arrows, so that means it has the most inductive effects. So it has the most electron density protecting this carbon, and this one has the least. Does that sort of kind of make sense now? Okay, yes. Yeah, so resonance tends to be a stronger effect in general than inductive effect. I wouldn't think of it that way. What I meant by like induction is, or resonance is like a stronger effect is like, let's say we compare number 1 and number 3, or A and C. So this one has 2 inductive effects going here, which, cool, that's 2 inductive effects, whereas here it's only 1 resonance effect. But this resonance is an actual movement of a lone pair of electrons, whereas this is just like sort of kind of a little bit of density sprinkled here and there. So this is a lot stronger of an effect than these two. That's why I said this 1 resonance effect trumps these 2 inductive effects. I saw you first, yeah. For just this region, yes. Someone else had a question? Yeah, what's up? So for the hydrogen one, the electronegative effects are pulling away from the hydrogen. So all of these effects are pulling electron density away from the hydrogen. Whereas in the carbon NMR, they're still pulling away from the hydrogen, but they're pulling towards the carbon. Because it's going ultimately up to the oxygen. So it has to pass the carbon. Yes. Yeah. Yes. Exactly. So most is shielded. So they're flip-flopped. All right. Yes. That's for hydrogen NMR.
Yes, it's not.
This one is hydrogen. This one is carbon. So in hydrogen NMR, this one is going to be the most deshielded because this resonance is going away from the hydrogen, which is what we care about. We don't care about the carbon here. We just care about the hydrogen. I got an okay. Does that kind of make sense a little more? This one? Yeah. So same kind of thing here. This one is a higher number because it's more deshielded. And so this one is a lower number because it's more shielded in comparison. Yes? Yes. Okay, that's the last thing I wanted to cover today. No, that's a perfect segue. Thank you. And then what was your name again? Evelyn? I will try so hard to remember that. Okay. You think I'm joking, but the other day I went to see a movie, and the movie ended, and I didn't know the main character's name. So, it's really bad. All right, so we're going to do a conversion between ppm and hertz and megahertz, right? Does anyone know the conversion equation? What are you sorry for? You get this, girl.
I think it's like whatever the frequency of.
I'm impressed you know that, but that's too complicated for us. We're doing an even simpler one. I think you had your hand raised. Oh, okay. Yes. So close. Yes. Okay. So we're going to say ppm equals hertz over megahertz. And I'm getting there. Okay. Times 10 to the 6th. Technically, it's times 10 to the 6th. But please trust me when I say we don't need this. In this class, he will give it to you so that the units check out and everything converts properly. Please do not multiply by 10 to the 6th. Please. You will not get the right answer. No, he probably won't even do that, if I'm being completely real. So while technically, yes, it is times 10 to the 6th, we're going to trust Rosemary on this one, and we're going to just cut that out of the equation. Okay, and what was your name? Stephanie. So as Stephanie said, these are just things. What do they mean? So hertz is basically going to be the observed frequency. Megahertz is the spectrometer. And ppm is the chemical shift. It's okay. Alrighty. So that being said, let's set up this question and answer it really quick because I know we're almost out of time. We can do it in a minute. That's fine. So, ppm, what is it? Awesome, but I meant in this question, what is it? 1.25, yes. 1.25. Okay, so which are we missing? Hertz or megahertz? Hertz. So we do x over, what's the megahertz value? 400. Okay, now someone, be a math whiz, multiply 400 by 1.25. Swag. Your observed frequency is 500 hertz. Ta-da! Wow, thank you. How do we feel about the stuff we covered today? Okay, do you feel better or worse than when you walked in here today? That's always good to hear. All right. So oh my gosh, you guys can feel my pictures. Oh. Okay, please try to sign in again if you weren't able to, and if not, I will email you a link. Yeah. Yeah, of course. Here, let me just